Have you ever stopped to think about how your computer actually, well, thinks? It doesn't use words like you and me. It has its own secret language. And this language is so incredibly simple, it only has 2 letters. Just 2. Yet with those 2 little letters, it builds your entire digital world. We're talking every photo, every song, every single message. So today, let's learn that secret language.
It really does seem impossible, right? I mean, how can a simple machine that only gets on and off hold on to your most complex, colorful memories? How does it create this entire digital universe we live in? Well, the answer is surprisingly simple. And honestly, it's kind of brilliant.
To get our heads around the computer's language, we have to start with this idea of data. By itself, data is just stuff. It's raw, unprocessed, unorganized facts. Think of it like a giant pile of Lego bricks with no instruction manual. It's just the raw material. And for a computer, that raw material is even simpler than a single brick.
So, how does a computer take all that raw stuff and make sense of it? Well, it starts with an alphabet. But this isn't the alphabet you learned in school. Nope, the computer's alphabet only has 2 letters. And here it is, the fundamental building block of everything, the bit. A single bit is the absolute smallest piece of data a computer can possibly work with. You can think of it as the atom of the digital world. Literally everything you see on a screen is built from these tiny, tiny pieces. So what in the world is a bit? Well, it can only be one of 2 things, just like a light switch. A 0 just means the switch is off. There's no electrical current flowing. And a 1? You guessed it, the switch is on. Current is flowing. That's it. Off or on. 0 or 1. This is the entire alphabet. Simple as that. And from these 2 simple states, everything is built. It's kind of mind-blowing when you think about it. Every photo, every document, every video, at its very core, is just an incredibly long sequence of these 1s and 0s. It's a 2-letter alphabet that writes every single story in our digital world.
Now, 1 letter on its own isn't super useful, right? So, computers group them together to form words. And the standard grouping is a little team of 8 bits. This team is called a byte. So by combining 8 of these on or off switches, a computer can suddenly represent much more complex information.
And of course, once you have words, you can start telling bigger and bigger stories. So let's take a look at how this all scales up, from just a single byte to the massive amounts of data we deal with every single day. You've definitely heard these terms before: kilobyte, megabyte, gigabyte, terabyte. They're all just names for bigger and bigger collections of bytes. You know, a really short email might be a few kilobytes, your favorite song is probably a few megabytes, and a full movie could be several gigabytes. Each step up is a huge leap in the amount of information. But hang on, look closely at those numbers. What's the magic number here? It's 1024, not a nice round 1000. Why is that? Well, it's because computers think in powers of 2. And it just so happens that 1024 is exactly 2 to the power of 10. See? It all comes back to that fundamental on or off nature of the bit. Okay, so we get it. Computers store everything as 1s and 0s. But how does a string of switches actually become a number we recognize? How does on, off, off turn into the price of something you buy online? Let's decode one together and see the magic happen.
All right, here's our secret code. It's a 1-byte number, 11001010. Right now, it probably just looks like a random string of numbers. But stick with me, because we're about to translate it into a number you'll recognize in a heartbeat.
Whoa, okay, this table looks like a lot, but trust me, it's our official decoder ring. Let's break it down real quick. Up at the top, you see our number, 11001010. Simple enough. Now, the magic is all in that bottom row, the place value. Check it out. Each position, starting from the right, has a specific value that just doubles each time. 1, then 2, then 4, 8, 16, and so on, all the way up to 128. These are our powers of 2.
So here's the game plan, and it's actually pretty simple. We only care about the columns where the binary digit is a 1, where the switch is on. If there's a 0 in a column, we just ignore it completely. So we just find all the on switches, grab their place value from the bottom of our table, and add them all up. That's it. So here's the math all laid out. Just like we said, we've got a 1 in the 128th place, a 1 in the 64's place, another 1 in the 8th place, and one more 1 in the 2's place. We're just going to add those values together. The others are zeros, so we can forget about them. So what do we get when we add it all up?
We've got 128 plus 64 plus 8 plus 2, which equals 202. And just like that, the secret code is cracked. That meaningless-looking string of ones and zeros translates perfectly to a number we all know and understand. Pretty cool, huh?
You know, this system is the absolute bedrock of our entire digital world, but it's not a new idea, not by a long shot. So whose brilliant mind first dreamed this all up?
Well, the basic idea of a base 2 system goes way back to 1689 and this genius polymath, Gottfried Leibniz. But the really crucial connection, the big aha moment, happened in 1937. A mathematician named Claude Shannon, and what might be the most important master's thesis ever written, showed how this binary logic could be built using simple electrical circuits. He's the one who connected the abstract math to the physical world, and in doing so, he basically paved the way for every computer that came after.
So let's wrap our heads around this for a second. We've seen how any number is just a pattern of switches, but that means everything is. Every word you type, every color in a photograph, every single note in a song. At the end of the day, it's all just a really, really long string of ones and zeros. So if all of our most complex and meaningful information can be built from the simplest possible choice, on or off, yes or no, what does that tell us about the nature of information itself? Something to think about.